Hi, this is our ECE Fund 2 final project. I'm Fee Lu.
I'm Ethan Jacobson.
I'm Casey Ladd.
Starting with the purpose and goals, the purpose of the project aims to create a system that uses and analyzes audio input from a song and separates the sound frequencies into high and low frequency parts. The frequency components of the song will be visually represented through a green and red LED. Our goal was to gain a deeper understanding of breaking down a complicated system and analyzing each subsystem and its design values by applying techniques learned in class to finally combine and produce a functioning light show. To solve the system, we broke down the system into blocks to simplify analytical analysis.
These systems are the summing amplifier, the low pass filter, the high pass filter, the two peak detectors, and the two LED drivers, as well as the powering circuits.
For our summing amp, the purpose of this subsystem is to sum up the input stereo audio signals, as well as remove any DC bias that's less than 20 hertz. And moving on to our next subsystems, we have Sallen key filters. The first one here is the high pass filter, where using the components here, we picked out a break frequency for our signal to be, for our audio signal to be 650 hertz. And so in this high pass filter, anything that's less than 650 hertz will be attenuated, while anything greater than that will be passed. And for the low pass filter, it is vice versa. Anything less than 650 hertz will be passed, while anything greater than that will be attenuated.
The peak detector circuits are responsible for taking in the signals outputted by the high pass and low pass filter and smoothing them into almost DC waveform that will later drive our LED drivers and turn them on. To do that, we first pass it through a capacitor, eliminating any DC impedance. Next, we have a voltage divider here. What this does is it sets a positive DC source after eliminating of the capacitor to right at the future MOSFET's cutoff between the cutoff region and saturation region. What this does is that any signal coming in from our low or high pass filters will turn on the LED using the LED driver. The signal is processed into something called a peak detector using this super diode circuit. What this does is it removes any negative voltage that would reduce it, makes it all positive. This op amp combined with the diode makes it so there's no voltage reduction from passing through the diode. Next, we have a filter configuration designed to set the time constant of our peak detector. This is what physically smooths out the signal into a DC waveform. All this leads into our LED driver, which is a MOSFET. The signal from the peak detector comes into the gate of the MOSFET, and so when a signal is applied, it reaches the saturation region, turning on the MOSFET into a voltage-controlled current source. So essentially, as the louder the volume gets, the brighter the LED will get. And so when the MOSFET is enabled, current will flow from VCC to VE to the LED. I'll now present a video of our board in action. An important takeaway from this video is that during the build up to the beat drop, the green LED got brighter and brighter as the frequency got higher. And when the beat actually did drop, the red LED came on very bright as the low frequencies came on. Oh, the challenges faced are including the final subsystem testing. After we soldered all the components to the board, we needed to verify that each subsystem worked. We did this by disconnecting shunts between segments the J2 connectors. However, powering each segment and figuring out the output is difficult, especially for the LED segments, where when the shunts were removed, the LEDs would act strange and almost overcurrent. So it's difficult to test the LED drivers independently.
The other challenges that we were facing were when we were creating the peak detector and LED driver component selections. One of the issues was during our creation of our low pass filter after the super diode. And so what was happening is that if we were using a capacitor that was too small, then the current that was and the voltage, the gate voltage that was created for the MOSFET was too short of the threshold voltage, causing the current in the LED to and the light of the LED to flicker too much as with constant frequency. By increasing our capacitance of our capacitor in the low pass filter, that smooth out the current and signal better, and so kept the LED at a more stable brightness.
Key takeaway that we learned was that all models are wrong and some models are useful. We use models to create accurate approximations and representations of the system, since it's impossible to create a model that perfectly describes the real system. However, these models can also be extremely helpful in understanding and predicting the behavior of the system. For example, with the MOSFET models are simplified representations of an intricate device, but it helped us determine the calculations needed to determine the proper design values.
Going on that, subsystem testing to verify our analytical models is also required. Examine with the MOSFET and the LED driver. Those models relied on simplified abstractions of a diode and a MOSFET respectively, which are nonlinear devices. So using a linear model to approximate, we get convenient values and are able to calculate our resistors and capacitors that we need. However, as one of our challenges suggested, the models are wrong. We needed to have a bigger capacitor, and for the red LED, a much bigger resistor as well.
And the last thing that we learned is that numerical analysis is just as important as experimental analysis. This is mainly for debugging, as sometimes if we were to move straight to experimental analysis without using a software-based analysis like multisim to test our resistor and capacitor values that we have chosen for any of the subsystems, then it's a lot harder to fix them in the experimental analysis when having to replace these parts and then use it as well as using the breadboard. And so to emphasize this point is that using multisim and other software for numerical analysis makes debugging these subsystems easier.
All right, thank you.